So let's take a look what we're going to learn. Electromagnetic induction today. Well, induction, this means current was induced, right? From the magnetic field, right? But how exactly that happened? Let's take a look at what exactly happened at that time. Well, right before it, actually 10 years before that, we find if we have current in here, we can find there must be magnetic field in there, right? That for sure. And then later people find this could also have create magnetic field. It's only natural to guess that maybe I can create current from magnetic field. But that took at least 10 years probably. And let's take a look at the key character Faraday. And the important thing is that we don't think that we're smarter, right? That they took so many years. Not only him, a lot of other great scientists too. What they actually do is use this is this battery. This is what a radio looks like at that time. And this is the primary core, and this is the secondary core. So this is basically the magnet. Right now you can see we normally just, do it like this. And then get a magnet to get in. Same thing as Faraday's. At the time he just thought, current can create current. So he didn't really know is actually just using a magnet is actually probably better. He's using it up and down, up and down, up and down. And then got a meter there to read whether there is current or not. Well, we use a light bulb. Well, it's probably used that because there was, quite a little tragic accident there, so which make him, use so many years. Let's see a little bit more. Oh, this is basically Faraday's law of inductions, that experiment. These are used in different directions. I use this one, it's kind of easier. This is the magnet there. And then you can see the voltmeter in there. At that time, sadly, for Faraday, it's like this. This is the one, and if this is the magnet to get in, sometimes saying this is the meter on the other side, this is the meter on the other side. The sad things, the meter only moved for a second. The sad things, you look at this and then look at this. Sadly, that took so many years. Later, he look at this and then look at this, and then he find it. Combined with a lot of other factors for it. Here's another one. This is North Pole, this is South Pole, and here's a magnetic field, and this is a conductor. And then you move it in here. Well, if you have, you can also have the current in there and find the voltage in there, right? So now we call it cut through the magnetic field. It's kind of like this is your magnetic field and just cut it, right? Cut it. This is the conductor. Cut it. Now we know this can make current inductance happen in there. And now let's take a look at, this is PTET. I'm only taking a picture saying there. At that time, the thing is, if you only put in there slowly in here, the light is not shining. If you put it in there, it's not shining. For example, next picture I have this. See, still no, only in here. What's the difference? Why the light bulb is shining in here? It's because you do it fast. If you do it fast enough, you have to change it. So the changing is the key character now. Huh? Now we know. And also look at the meter or look at the ball at the right time. If you look at later, it's maybe 1 second gap and you wouldn't see. What else is related? They must try so many other like factors and variables. Yeah, for example, they make more turns of the coil. Yeah, that happens, right? They already know that at a time. More turns, of course, probably more current, right? So what are the factors in here? In here. So now they find the voltage is related to something like this. If it is like this, related to the length of the wire inside the field. It relates to B, the magnetic field strength. It relates to the velocity, how fast you cut. As I said, how fast is important. The time is also related. How fast is important. Not only you move, you have to move kind of fast, hopefully. And then the second one, Faraday's induction, is, well, if I make this one bigger, you can imagine the cross-sectional area is also important. More and more current in there, more voltage in there. And if the magnetic field is stronger, or you can say magnetic flux density is stronger. Oh, we're going to talk about this later. And the number of turns is important. That is already known at the time. And also, as I said, how fast the coil turns into the field. How fast? That's important. So time is also related. So let's see more. And if you find the voltage, it's actually connected with the data. So it matches. Which is these two formula actually or checks later. So this is a cross product. It's not just a vector. Newton already liked vector a lot, so they have a lot of help from the vector mathematical knowledge in there. So they use cross product there. So also gonna help out with the direction later. Well, these two actually can be the same. How? For example, if I change this in another direction, it would be, say this is the rod, metal rod, and say this is the direction of the field. If I move it in there, say I move it in here. So if this is X, this is L. So if I use the time delta t, you can see that if I'm using this one, of course, n is 1. So I can just use delta n is 1. So B is the same, right? B is not changing. B is the same. And I can also say delta A. Delta A is basically X time L, right? It's X time L. And divided by delta T. Isn't that velocity in here? This is B velocity L. So this one is working. So this one is basically a special case for that one. So now everything comes down that we all have BA. So what's that BA? So now it's not only magnetic field strength, it's actually going to be something else. Here. Now, before Faraday thought is the current somehow create current. Now it's the BA is important. If BA is changing, so that's why it's delta NBA, right? It's changing. That's important. So we give it a name. BA is flux, is magnetic flux, and it's basically is how many field lines are in the plane or in the area, right? How many are in the area, right? How many are in the area? Is it only a few or is a lot, right? It's different, right? So that is related, the phi. We're gonna name phi. Not only is B is important, now we get more data. You can imagine they have so many data, right? Of course, you can get the voltage or the EMF, right? And you can have what B is important, right? Actually, B perpendicular, which means B is the component of the magnetic flux density. This is called flux density now. Is perpendicular to the area. It's not just this is the flux density. It's not just magnetic field. It's the flux density we call it now. But also, why we call it perpendicular? Because if you don't use perpendicular, what will happen? What will happen is if it's like this. And suddenly the equation is not working. And later people find out, no, it's not. Faraday's or Maxwell, they find out it's not like it's not working. It's like you should use this. For example, this is B. You should find this is perpendicular to that plane. And that is B times cosine. See? B times cosine theta. And that's the important component. So B is the component perpendicular to the area. But flux density. Of course, you can use like 1 Newton over like ampere times meter. But in here, we say this is more important. So we call it Weber. 1 Weber is like a 1 centimeter, 1 meter squared. So magnetic flux density is 1 T, Tesla. So this is a key factor in here. So this thing changed. How fast that thing changed? Huh? It's delta phi over delta T, right? Only times delta N. And now let's see a little bit more. Now let's talk about how do you change the direction. As I said it later, after that experiment, we find out this is more like it. If you cut through the wire, this is like this. If you cut through the wire, it's like this. If this is cross product working, if it's cross product, this is a vector product. So I'm going to use the things that we learned in math, right? This is the first direction of the velocity direction is in here. And then turn into that, this is the magnetic field direction, right? It's like this. Hey, let me mark it a little. Direction is in here. And then this direction is in here. The first one is V in here. And I got to turn in there. Oh, there. Because I'm in here. Well, I'm in here. And then I'm changing it in there, right? I go in there, right? Or I can go in there. Right there. Right there. Yeah, this is the one. Yeah. So there's a cross product, right? We can check it in here too. This in there. Oh, there. That feels better. This one is a reaction. Oh, I don't want to twist it too much. So I got the motion in here, and then I want to go there, right? So that's my direction. I still that first. And then I can use this. I can use this one as a demonstration of the direction, saying this is the velocity, is the direction of the motion is upward. This is the first one, and then I cross to there, right? So this one is going to be the direction of the induction of the EMF. And then if I use coil, when using this, then is not the generator that Faraday used, but this one is more like the AC alternating current generator that we use these days. I can still use like, if I turn like this is the direction, right? This is the direction, and the field is in there, so it should be this, right? This is in there, yeah, it's in there. So it's A to B, right? This is the direction. This is the direction of the current, and in this way, I'm turning downward. So the first velocity direction is in here, and then I'm using that way, right? I'm using this way to turn it, to rotate to the second direction. Okay. So this is gonna be another current, right? So this is gonna help us to find basically mostly what we use the alternating generator these days. I can check it with this too. I can check it with this. Still V is in here, velocity is in here, and that is in there. I'm gonna use there, and the direction of the magnetic field is where? Looks strange though. Yeah, this is the way, because it's in there. In there. Oh, there. Yeah, yeah, this is the one. And then you go. Yeah, this is the one you go. Next one. Oh, since this is the generator, let's take a look at the generator, like the alternating current generator, since it's related to what we're using here. Oh, this one is actually, I already proved it a little, so I don't really need it now, I guess. Oh, this is still that. People find that, you can see, this is what we just did it, right? So you go in there, you get a current in there, you get a current there. Don't I just have like a battery in here? Kind of. I can provide for the electricity, right? What I actually wanted, so I wanted to all kinds of, for example, if this is an AC generator, see this is an AC generator, this is the way to go, right? This is the way to go. Same thing, this is look a little bit better. See, how is it going to be changed? Now, they have several things I would mention a little. This is called the pushes, and this is called commutator. What we actually find the data is more like this. For example, if I start to collect the data in here, so t is equal to 0 from this moment, because I'm turning this, right? I'm using, there is something that I can do it like that. See, this is turning, and t equals to 0 is 0 at that time, and then more and more. See, this is t equals to t over 4. Here, t equals to t over 4. And then a little bit more. Ooh, a little bit more. A little bit more. A little bit more. See? Let's take a look at this. Turn, 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 turn. So that's why we call it alternating current, right? Yeah, we're gonna explain a little bit why it's just looking like that. Well, not enough time. So we have we learned a little bit BA phi, right? And thank Faraday they said this changes the rate of this thing is got to relate to EMF. And this is the new unit. And N term is important in phi. And this is going to be the EMF, induced EMF, and a little bit AC generator. Now we're going to keep talking about the AC generator a little bit later. Now let's just end it now today. Bye.